Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're going to talk about magic batteries versus real solution. So let's dive deep into it. Now, before we dive deep into it, we must understand why do we need battery this badly. Now, here's the there are two groups of people and both will agree that they need this. So let's dive deep into it. First group who believes in global warming. So you do not need to cook off the only planet we inhabit. And I can agree with that. You're like, hey, we have one Earth, there is no backup. How about let's not roast this? So that's one group of people. They're like, yeah, we really need to tame our CO2 side effects. Okay, that's one thing. Second group who does not care about that. Here's the deal. But what will they agree with? They will agree with cheap and abundant power. Now be mindful, there is one third group of random brain-dead people who are like, we have to reduce population. It's like literally, oh, you have a slip disc problem. Have you tried poofing yourself? Then you will problem will be gone. No, we have this to solve problem, and yes, it's a good thing we have problem. We're supposed to solve it. So first group who want to save the planet, second group who wants to save their pockets. Cheap and abundant power is a desirable thing. We have to figure out a way where it remains abundant and cheap. Now, fossil fuel, right? You will think, hey, fossil fuel solves the problem. No, it does not. It never has, it never will. Fossil fuel price will always go up because supplies will always run dry. Meaning, you're like, oh, Earth has more than enough oil. Technically, yes. But realistically, no. Meaning, does India have coal? Yes. Then why the heck Indian coal prices are going up? Well, the easily exploitable coal, meaning, oh, there's just giant coal seam, we can just mine it, it's barely few feet below the ground, we good. Yeah, we did that. And then it ran out. Then we have to dig deeper. Now spend more money, more energy, more time to get into that. Now extract that. And then it's like even deeper. So all basically available, it's not available to us seamlessly. So early exploiters, we always get the benefit. For example, in 1920s, there are places you just like oil. I'm not even joking. Like they were doing water well, and it's like voila, oil. But that will not happen. Again, I think 1950 is a bit too late for that, but you get the point. It was super easy. India had oil wells, but it ran out. The first few years, you have that easy to explore area. All of those have been exploited. So at this point in time, it's harder. We are getting desperate to extract it. Not the amount. Amount is there, more than enough. It's just that now we have to extract it from shell layer. Can we do that? Of course. Now the price is higher. So that's why the line always goes up. Does not matter what thing you're talking about. Does not matter you're talking about oil. Does not matter whether you're talking about gas. Does not matter you're talking about coal. It will always go up in price. For example, this is India's petrol and diesel prices. Same thing will apply with every nation. You can check for yourself. So, and yes, that will also apply in OPEC nations. Again, the rate will be slower, but it still will be there. So, for example, in the early days, as in 2004, I remember vaguely, so to say, petrol was 35 rupees and diesel was 22 rupees. In contrast, right now, 2024, petrol is 106, diesel is 90. Line went 2 up. So, as you can see, fossil fuel will never ever be cheap. It could be abundant. Technically, it is. It's just that it's not cheap and abundant. Meaning, if you rely your country on these things, your food prices will keep going up because, again, your tractors will consume. So, in 2016, your tractor will consume this sort of energy. In 2023, it will consume far more energy, as in like costlier energy. So, cheap part would be forfeited. Penalty of that would be abundant part would be forfeited. So fundamentally, that's why we have to go to renewables. Now, do we have real world data? Like these are real world data. Do we have real world data that proves without a shadow of doubt that renewables gets cheaper? Yes. This is solar from 2010. So solar basically dollar per watt was $2. Now again, assume whatever you want to assume that line was here. Now here's the deal. This is 2010. We start to deploy more and more. Inflation is going up. Like 2010 is not a very ancient times. It's like not even 19. So 2010 and 2020. Now we have bonkersly large amount of solar installation. However, the prices are going down. As in 2020, you are spending money. You may be spending more money, but you are getting more watts out of it. It's actually getting cheaper. The line is going down, not line is going up. Oh, and another thing, if any Tom, Dick and Harry opens their mouth for nuclear line always goes up. That's why you do not want nuclear. You always want solar and wind because line goes down. Now, let that be very clear. The early days of solar panel were very polluting because we were figuring things out. And for some reason, people forget it's like, oh, coal. Like, you remember during the time of Edison and Tesla, what was the coal power plant efficiency? 1%. It takes time. We spent 1 century refining these puppies, and then you're like, hey, renewables are not that efficient, man. For it has been like 5 minutes old and it's not genius. It's like it takes time. Solar panels that were in the early 1990s, they were not good. They were good for satellites, but they were not good in terms of energy production. 2010, barely. The carbon footprint was starting to come down, but barely. More efficient, more mass production, more research, more development. Now we have carbon footprint that is so low that at this point in time, there is no other source that has that low of a carbon footprint and that amount of energy output. That is today. Wind farm, same thing. People will give you, oh, the wind farm consumes so much. Yeah, the early wind farms did that. Like wind farm that are like 1 megawatt or 2 megawatt, they were dirty as hell. We had to spend time. We had to go from 1990 to 2000 to 2010. The better research, better development, better analysis, all of that, and better prediction also. All of them allowed us to now build turbines that are 12 megawatt Sylvain turbine, 16 megawatt. I think that's General Electric Halide X. So we are learning, improving, and the carbon footprint is becoming better. Again, same way, it's like, oil refinery is not like a one-day product. It's like it took a century to make it that good. We used to put lead into it. And then we learned, yeah, that's not a good idea. So same thing will happen with renewables. So any Tom, Dick, and Harry is like, oh, renewables is polluting. Of course, in the early days, it's supposed to be. It would be. We keep working at it and we keep it. And line goes down. Line goes up. Choice is yours. Do you want to live in a world where you can afford cheap food, or do you want to live in a world where you starve to death? Your choice. Money-wise. I do not give a damn about planet. So again, that's why I said there are only 3 groups of people. First group of people, they do not believe in renewable, environment. Still, you give a damn about your pocket, and people who want to give a damn, there's a very good thing. You should move into this direction. And then we have third group of brain damaged people who are like, what if we poof the humans? It's like, what's the point of you living then? Now here's the deal. If this is so sorted, like, ancient time, 2020, then why haven't we done it? Well, there are 2 missing links. If you do not have storage, be mindful, solar and wind has crossed that threshold, crossed the Rubicon, so to say, where now if any Tom, Dick, and Harry opens their mouth and say like solar and wind does not have enough oomph to drive a nation, yeah, no, they have to. Flat out. We have crossed that point. Like nobody is saying that we do not have enough oomph. Be it America, be it India, be it China. We crossed that point. The problem is, those are moody. Meaning you may get boatload of solar today, you may not. You may get boatload of wind, but you may not. So that's a problem. And we are also moody. So supply is moody. Demand is also moody. So you have to somehow manage these 2 puppies. How do you manage that? You need storage. That's the missing link as of now. Again, I'll talk why it was never a missing link. It was just tech bro brain damage. But we need storage. On top of that, another aspect that yes, that was missing, we were never thinking about it, was inertia. Meaning the reason why our grid works is like, think in this way. Everything is fine, everything is dandy, and you turn on a 10 megawatt furnace, which is not that big, but again, there are many. You turn it on. Where the heck that 10 megawatt came from? Because you did not pick up a phone and call the power plant. It's like, bro, increase your output by 10 megawatts. So where did that power come from? It came from inertia. Meaning your equipment consumed power from the magnetic field of the transformer. It's like leached that energy. Where did transformer leached it from? High voltage lines. It leached it. Where did high voltage from? Leached it from the power plant substation. As in its high side. Where it leached from? Low side of the generator. Now, where did that generator give the energy from? Rotation. The magnetic energy was leached from the rotational energy. Now, here's the deal. What should that happen? Energy cannot be created nor destroyed. Meaning the RPM should go down, right? So, if let's say it's India, RPM is 50 hertz, 1500 RPM, it's supposed to slow down. It didn't. Why? Well, inertia. Every motor, every generator, every turbine that is spinning, it's spinning in what we call synchronous mode. Meaning collectively, there is hundreds of tons that are spinning. You cannot slow down hundreds of tons like this. You can turn on a switch of 10 megawatt, but you cannot slow down that. Now, what does that mean? That simply means that instantaneous slowing down does not happen and it slows down. Now, that slowdown is stretched. Meaning your computers can look into it. It's like, I'm sleeping, and it's like, hey, wait a minute. Why the turbine is going from 1500, perfect 1500, to it's like, 1490. Okay, it has dropped to 1480. Yeah, okay, increase the steam pressure. That's how our grid works. So without inertia, your grid is not stable. It's cool and all for having a solar inverter that takes care of your house, but running a nation without inertia is not an option. Your grid will go kaput if you do that stupidity. We never had to thought about that, but now we do. We have to figure out, because solar and wind gives us cheap energy, abundant power. But without storage and without inertia, they are non-usable to us. So again, if you do not know about this, people will bitch slap you, and again, people will go back to these things. So we have to solve this. This is a critical reality. We must solve the storage part and we must solve the inertia part. Without that, we dead. So what is this magic part? Now here's the when this aspect was realized in let's say 2005 to 2010, a race was created, like bonkersly large amount of research paper, bonkersly large amount of seed funding. There was a whole race to make the battery of the future, quote unquote. And money was spent like there is no tomorrow. And again, you would want that, because again, we are trying to save the earth. Bill Gates was spent boatload of money, Elon Musk spent boatload of money, Jeff Bezos spent boatload of money. People were spending money like there is no tomorrow. They went all out. And weird battery designs came out. For example, molten liquid battery from like Ambria battery. The idea was like, what if you have metals, right? Metals are very good ion condenser in liquid state. Problem is metal require very high temperature to be in liquid state. Even sodium could require as high as 200 degrees Celsius. Other metals could require as high as 700 degrees Celsius. But if you have that, because you have gravity, you have this advantage that if you have three materials, let's say anode, cathode, and separator, it will never touch each other. Why? Gravity. If you put water and oil, why do they separate out very quickly? Because of gravity. So what happens in a molten state? Because of density, things separate out. So ions move. Now, because in molten metal state, molten pure metal state, the ion movement is exponentially better. Meaning a battery that is like, fixed size, the energy density would be damn high. Meaning you think lithium ion is high, this is like, bro, I got this. This is much higher. Energy density, energy capacity, and in terms of lifespan, yeah, there is no inherent limit, meaning it can last forever. Technically, let's say worst case scenario happened. The insulation, that fire brick insulation cracked. Okay, it started to cool down, it will froze up. Okay, what does that mean? That simply means replace the insulation and start to melt it again. Ta-da! Nothing else, because again, it likes to be cycled properly from 0% to 100%. It likes that. It does not have oh, we have dendrite formation, liquid metal, man. Gravity is like, nah. Dendrite is going into high density place, no, go back up. Gravity is like, nah, bro. And liquid state of high temperature metals are like, nah, bro, everything is cool, bro, relatively speaking. So interesting concept. It's just that until you realize that it's so ancient that it was tried by Henry Ford for Model T battery modeled. So molten liquid is there. Then you have liquid redox flow battery. Again, inherently a good concept. The idea is that you have a battery that is independent. It's basically a generator, meaning you can control the output and you can control the duration. As in the kilowatt hour or megawatt hour can be controlled, and the megawatt is also controlled. For example, how much oomph you get, how much reactor area you have, how long you run it, basically the tank size, and it can be recharged with a liquid. Basically, you in principle could charge up from the summer and discharge it in winter. It can be done. Again, old idea and scientifically true. Nothing here is non-scientific or like it would not work. All of them are real, practical things. Some have been in used. And then we have nickel hydrogen battery. Again, ancient technology has been used in ISS, Hubble Space Telescope, ancient technology. So problem was like, it's good and all, but it requires very complicated metals like platinum. So other companies like, okay, we can change the metal. Then you have aluminum air battery. Again, ancient technology, but so many happened. Now here's the deal. I started, again, I have in my channel, you will find most of them being covered. But now I'm realizing that if it's that old, there is a very good reason why it did not work. Because if you do not know the history, you will think hydrogen is a new technology. If you know the history, you'll be like, bro, we had hydrogen fuel cell that went to the moon, 1969. We had hydrogen in basically space shuttle. Then NASA abandoned it. And again, we had hydrogen plane, we had hydrogen train, we had hydrogen fighter jet, hydrogen car, hydrogen combustion car, hydrogen fuel cell, all of that. Then we abandoned it. Then in 1990, Sony brings out a patent of lithium ion. Then lithium ion starts to being mass produced, and then people are like, whoa. That means maybe, just maybe, lithium ion is a good technology. And all the technology that we have been abandoning, there was a reason to abandon it. For example, this Ambria battery. Yeah, you must have seen boatload of videos about this. Like, this is a good technology and all that. Again, real scientific thing. Bill Gates poured money into it, and every YouTuber just went YOLO on it. And then you're like, okay, why the heck no video is there after for 2 years? Yeah, they went bankrupt. Their latest website says they have recovered from Chapter 11 bankruptcy, whatever that means. So that's the whole point. It's like we are trying to reinvent things even though market, again, physics, engineering, economics is very clear. Lithium ion works, lead acid works. Everything else is very niche case. So many more new technologies. Again, these are just few examples, many more. And here's the problem with all of them. None of them can provide inertia, meaning none of them are quality material for running your national grid. You are just trusting at that point your inverters to be good, which... So what are our options? Well, first option is real world. Pumped hydro. Now, pumped hydro is the oldest technology known to man for large-scale energy storage. And here's the personal benefit. This was ancient technology. So it was built in an era where you're supposed to have inertia in the grid from the source side. But here's the deal. What if the source is not enough? How would you get energy and inertia? This has discharge inertia, meaning when it's discharging, it's literally like a dam, meaning you have a water mass flowing, which is spinning. Like water is non-compressible. So it has like oomph to it. Then you have turbine, which is again hundreds of ton. Oomph. And then you have motor rotor magnetically coupling. So you have physical inertia when you're discharging it. And when was the first time we invented this magic technology? 1907. 1907. That's when we first actually built it. It's a small unit for that time, but we learned it. And you were like, okay, you must have seen people who are orgasming when Elon Musk said, like, this is long ago, like 2016 ago, or maybe even earlier than that. It's like, you know, we're going to build with Panasonic the giga battery factory, and like we need 8 or 9 of that to solve the world energy problem. Everybody was like, you know, whoa. And I'm like, come to Earth. 1 gigawatt hour, which is huge. Google how many battery plants, chemical-based battery plant or like, you know, lithium-ion battery plants can touch that. That was achieved in 1929 in Germany. It's ancient technology. 1 gigawatt hour. 1929. And you're like, what the hell happened in after that? Well, then America went like, and this is the old America, it's like mine's bigger than yours. So they made Bath County pump storage, which is again still working right now. And it was a bit more oomfish. How much oomfish? 3 gigawatt was the power capacity, meaning how much oomph it can dump? It was 3 gigawatt. Now, like, okay, what if it's like, you know, very small capacity? 24 gigawatt hour capacity. There is only one thing that is higher than that, and that is Chinese grid pumped storage. Nothing comes close to it. And when did we make this ancient like black magic technology? 1985. Now you're like, okay, 85 sounds weird. Yeah, this is when people had the nuclear fever. This is like post end of that nuclear fever, because in nuclear people realized, okay, assuming they did not know better, but assuming that we all go into nuclear, problem would be you have to make way too much nuclear, which will reduce the ROI of all the plants, or make enough of them that base load is covered, and then you fill the gaps with some other things. Then somebody came up with the idea, it's like, okay, what if you increase the base load so much that during night times it overproduces, during daytime it lacks. So nighttime will be charged into the pumped hydro, and then during daytime you discharge it. Day and night cycling. That's why the cycling of pumped hydro became such a common thing in 1970s and 80s. Bonkers amounts of plants were built, again, all around the world, even in Switzerland. So it went all in. Now, are there any fundamental law of physics penalty? Yes, it has few weak links. So one of the biggest weak link compared to a lithium ion battery is that poor round trip efficiency, meaning if you have a lithium ion battery that is good, well maintained, inverters are good, if you dumped 100 megawatt hour into it, you can get almost 95 or 92 bare minimum. You will get 92 megawatt hour out of it. So very high round trip efficiency. Here, if you are lucky and modern technology, you can reach 80%. That's upper limit of it. And again, some designs are there that should push it a bit more, but not much. So there is a penalty, meaning every time you're running, you're wasting a little bit of energy. Not too bad, but you have that. But what about other penalties? Other penalties, high capex, meaning you have to spend some, like I have linked a Switzerland video down there, that's a $2 billion. Now here's the 2 billion sound a lot until you see the capacity, and then you compare it to lithium and it's like free. And then you compare to lifespan, be mindful, 1985, still working, and capacity is the same. It does not have degradation. So, and one true penalty to this is government bureaucracy. Like, so much BS is going on in this, it's like, it's tragic. Like, we could have solved all the problem without even orgasming over, like, you know, giga battery factory, man. It's like we could have solved all of it, like all of it, with just government bureaucracy. That part is genuinely sad. It's like, why did humanity perish? Because we had government bureaucracy. And now, how long can it last? Again, given the fact that it's a real world thing, we have real world data, as long as you can maintain it. There is no inherent expiry date. And again, people upgrade it. For example, they had a system that was 75% round trip efficient, and they're like, okay, the motor generator unit has served its time, 30 years old. Now it's time to refurbish it or repair it or replace it with a new, more efficient design. It has been done in few of them, and it's like, now we get even more capacity. Same structure, more capacity. So as long as you can maintain it, you can keep using it. There is no inherent expiry date to it. There is no dendrite formation with a, separator piercing chemistry to it. It just works. And here's the deal. What if you do not want to destroy a river sphere? Again, we are running out of rivers. Again, it's places that are closer to equator. They are experiencing right now, aka India, China, Africa. We are experiencing that. Egypt. So we are like, okay, what can we do? Well, we can do closed loop system. Again, closed loop is also ancient, and it has a very low harm, meaning it will not cause a devastative disaster to the biosphere. That's good. And it is mobile also, meaning for environmentalists, low harm. That's the part you sell to environmentalists. To people with economics, you sell them mobility, meaning you can build it anywhere. Example, Israel. And you're like, okay, Israel does not sound like it has a boatload of water resource. That's the whole point. You can close loop it. You can do it anywhere. And if you are lucky, you can cover this with solar. And all the wastage in it, because again, solar will do dual duty. It will provide enough power to do auxiliary runs of everything. And again, you already have substations. So you have the electrical utility sorted anyway. And it will also shade the water. So evaporative loss will go down. So fundamentally, it is a tested, it's expensive. But again, on this scale, it's free. And it scales and it works for life. But it's boring, meaning I can easily get Australia excited on, oh, Elon Musk 100 megawatt hour battery. I cannot get Australia excited on pumped hydro that will work for centuries. Cannot. It's just that our tech bro, man, that whoa, man, that we are like stuck in that. We are child like, oh, new thing. It's like, sir, 1985, sir. No. 20 plus gigawatt hour, sir. No. So what about lithium ion battery? What about molten battery? What about flow cell battery? What about this blah, blah, blah? And that is like, water, turbine, pumps, working. And closed loop has far more availability. Like basically, locations you can choose is bonkersly high, more than enough. Like this inherently during discharge cycle takes care of more than enough. Like after, if your country does this, not like, thousands of gigafactory and then having hundreds of plants built up every day. It's like, bro, again, 24 gigawatt hour. India consumes around 400 gigawatt. So not that much. We do not need that much. So this is pumped hydro, the actual daddy that provides you with large capacity, gives you lifespan, and gives you inertia. Then we come to, what if during runtime, like that's the discharge time, what about charging time? Well, there we have ancient technology known as Flywheel, Synchronous, Condenser, not Flywheel energy storage, that goes back to battery. Basically, that goes to inverter. It's artificial inertia. I don't like that. So solar and wind does not have inertia, meaning does not matter how many megawatts you add, it does not have any inertia, meaning one glitch can literally take out gigawatts of the system out of line. Has that happened? Yes. In real life, it has happened where one inverter glitched and everything else started to collapse because they're like, these do not have their own inertia to compensate. So they are always like, hey, what is the original source? Well, some coal power plant that is working. So if that coal power plant malfunctions, or most likely generally they do not, is the inverter glitches out for microcore fault or like, silicon bridge rectifier frying itself, yeah, poof, or cascade failure happens. So same problem. The idea of having energy without the inertia was experienced with HVDC, right? HVDC is a better way of energy transmission. You can transmit for very long duration, distance, so to say. India is leading in it, China is leading in it. China has a link that is almost 3,000 kilometers, and that puppy transmits 12 gigawatt. But again, it can only be done on DC. You cannot transmit that much, that long with AC. It has to be done DC. And again, how long ago we knew this? Hey, time we knew this. And if you're like, how the heck they were converting it? Yeah, Google Mercury arc rectifiers. Interesting technology. So we knew that we can transmit it with DC, long distance, bury the cables, make it safe, war safe, everything is cool. But how the heck you get inertia again? Well, Flywheel Synchronous Condenser was the solution. And how long ago have we been using this? This, magical technology, 1910, 1910. That's how when we started to use this. Now, why we were using it back in those days? Well, power factor correction, meaning if you know for a fact that even if you have AC, basically DC source from HVDC, you convert it into AC, you no longer have that reactive energy into the system. Basically, power factor is free floating. It's not desirable. So at that point in time, having this sort of more synchronous condenser allows you to solve it. And it also improves grid stability, meaning whenever you are turning something on, it could have a surge current. And again, many things have that. So over time, you could have like fluctuations. Now, when you have an actual spinning mass, that's like, I got this. But when you do not, like at the end of HVDC, it does not have that. Something has to absorb that shocks without destabilizing the grid. This puppy is like, I got this. I have the spinning mass. I got this. Now, another benefit, which you may find it odd, it increases short circuit current. It's like, is that a good thing? Actually, yes, because all our grid infrastructure is built on high short circuit current. Meaning, if you have a solar inverter going poof and it does not give giant surge current, a circuit breaker may not trip. And yes, it has happened. We learned it the hard way that you do need SCR. Trust me, every power provider will tell you, bro, you need to have certain level of SCR. If you do not, we cannot isolate it quick enough. So there is a fundamental reason why you need good surge happening when you have a fault. You need stability, that mass stability, and power factor correction. So what is this? Like, what is actually going on into this 1910 technology? Well, it's a flywheel coupled to a DC fed AC synchronous motor. So it's a AC synchronous, not induction, synchronous, meaning the RPM is locked to the frequency of the grid. And the core, you can feed, basically the rotor, you feed DC current to it. Now, why would you want to feed it? Well, you control the magnetic strength. Benefit of that, you control the reactive and active power, basically power factor. You can make it lagging or leading, both, without changing anything. So this allows you to power factor correct it. And because now you have a flywheel to it, and be mindful, back in the old days, they did not even bother to add flywheel because these things are huge, 10 to 20 ton rotor on its own. So it's like it did not need that much. It's like, yeah, I'm spinning, man. It's just a free spinning motor that is a DC fed AC synchronous motor. It in itself is like, bro, I'm more than good enough. We used to build hundreds of these back in the old days. And sometimes people went a bit crazy with this. It's like, what if we put it in vacuum? I was like, what if we put it in magnetic bearings? What if we put superconductors into this? Yeah, we have went all out, and now we are going again all out. It's like, it's a good technology. So if you have a flywheel coupled with a DC fed AC synchronous motor, which are like, where could you find that? Every turbo generator is that same technology. It's a basically small battery. Now, how long can it run depends on the mass and tonnage, but you can get few seconds of run time on these things. Now, what's the benefit of few seconds of runtime? Well, this is during running time, meaning if you have solar farm and then you put the one or two the puppy of this, your solar farm actually has inertia. Everything is actually stable. And when you have like, some destabilizing them, basically somebody turning on something high surge, is like, I got this. I have the inertia to ride through it. And it resilience, meaning random fluctuation does not get amplified. It dampens it down. It's like, bro, chill. Because again, if you look into the, Britain has that power control room, and you can see the graph is not very stable. It's like, again, they have very sensitive instrument to make sure. But so even though it's 50 hertz, so in Britain that 50 hertz, it's almost like 49.9995. So it has a lot of noise to it. So this allows resilience to handle that noise, quote unquote, and then you have ride through capability, meaning if it did slow down, it does not trigger a collapse. Basically, it does not trigger everybody cuts it off. It allows for some duration to like just push through it. So you will have a brownout kind of scenario, but you will survive, like you can jump through it. So it's a very good technology to add to solar farm. HVDC would not work without it. So it's a known technology, and this is what Australia could have done, where it's like, Australia had that battery, Elon Musk's first battery, and everybody's like, that's awesome. It's giving the grid inertia. It's like real inertia. And in those sort of scenarios, you're hoping, again, the early days, it was basically, there is time when you reach saturation, meaning the inertia of the system is already maxed out. Let's say steam valves are fully open. You can't do much more after that, right? Everything is maxed out. And then somebody puts a surge load. Yeah, and again, surge load will dissipate, but in that duration, it could trigger a what we call blackout. Basically, grid starts to cut things. If in that time you can dump even a small energy burst, basically 50 megawatt of burst, it rides it through. That's what that grid was doing. Basically, battery storage was doing. Early days. Nowadays, you have grid forming inverters on them that force it a bit more. But again, you could have done this, and it would have just worked. And the only technology missing for this is like how do we can make much bigger flywheel, because again I do not know whether we can attach flywheel segments, because again transporting those heavy mass is an issue. And again Europe also did something very clever. There's like, hey, we have island nation, we have a lot of wind and we do not have inertia. It's like, hey, we have this abandoned coal power plant. It's like, oh, coal power plant generator is DC fed AC synchronous motor. What if we just replace the turbine part, add a flywheel to it? Ta-da! We have a actual control mechanism with actual true authentic inertia. So it's a very good technology. Many company makes this. Is ancient, basically from GE to ABB to Siemens to every Tom, Dick and Harry else. It's an old technology. It's like you can just pick up a phone and order it, or build it, convert your old abandoned coal power plants to this. So it's a very good technology, especially for short duration. Basically, you are on your grid stability right now. This is the right now solution. You have a solar farm. Again, it will waste some amount of energy unless you have like, superconductor and superconductor, magnetic float bearing and vacuum chambers. Then you will achieve like almost zero running current, almost like it's just free floating flywheel, man. So, but it does have some wastage, but overall benefit, it's so good, it makes the grid worth it. Again, every country is learning the hard way. It's like no more magical tech bro technology. What if 1910 technology? So this is what works. Known technology, tested, gives you for like, especially for under 5 second energy duration, this is more than good enough. And you're like, do we need 5 second battery? More than enough. And again, the inertia part is compulsory. So this is what it is. Now we come to another aspect, thermal energy storage. Now I have already shared, you can even check the global coal prices and it will always go up. Like it's one of those things that you have to understand. Even though planet Earth has an infinite amount of coal, it's not infinitely accessible. So basically day 1, super easy coal. Day 500, damn, it's hard to get coal. Day 5000, god damn it, coal is expensive. So be mindful. What does that mean? That simply means all the money that we are spending on coal power plants, eventually they will reach a point where we have to shut them down, because again, somebody will not stop smoking like, tech bro weed, and they're like, okay, what if we actually did pumped hydro? What if we did a synchronous condenser? We'll reach a point where we have to shut down coal, because again, if we keep running it, energy cost will be so high that people are like, we'll do our own solar because we can't afford this. It's already happening. So that's a very short-term investment countries are doing right now. Like India is pouring boatload of money into making coal power plants. One very powerful coal power plant is being built in Jharkhand, Karanpur. Karanpur has India's first air condenser coal power plant, meaning the power plant has air condenser, so it's not evaporating water in open loop. So water loss is much less. That's a good technology. Now, coal part will fade at some point, maybe 10 years from now, maybe 25 years from now, but it will happen. It will happen. So take the lowest average price versus high price, and I'm not taking the surge, this price. It's reaching a point where like, solar is like, bro, I'm gonna destroy you. Wind is like, bro, I'm catching up, I'm gonna destroy you. So it will reach a point where you have to shut them down. And again, once we solve the issue of inertia, it makes sense to shut them down. But SD, we pour so much money, billions of dollars into this, hundreds of plants. India itself has like, I think 240 plants. So all the assets are there. You have generator, which is AC inductively AC fed AC DC fed AC synchronous motors. You have that, and yes, motor and generator are the same thing. So it is there, and you have the substation, all the structures are there. So might as well reuse the asset. Well, what would be the benefit of doing so? Well, inertia. Meaning, instead of having the flywheel, what if you have the same steam turbine? You do not even change that. You just add graphite blocks with heating elements. Meaning, when you have wind, surplus wind, graphite blocks heats up. When you want to discharge it, you let steam running out of it, and then ta-da, you have steam running a turbine, spin mass, you have inertia, and everything works. Now, is there a penalty of doing that? Well, yes, you're going through like electrical energy to like phase change of water. Yeah, 30 to 35% energy recovery. It's not very efficient. It makes a pumped hydro look very efficient. So it's not very efficient, but it does work. That's the good part. It works. That's the good part. And you're like, okay, how would it work economically? If you're buying 100 megawatt hour and you're only able to sell 30, you have to understand, because of renewable, especially right now, and you can check into California duck curve, there is 3 hours of time where almost all power prices are going to zero. Why? They are reaching curtailment, meaning you can buy power at that point in time dirt cheap, because here's the deal, what's better than zero? any number is better than 0. So even if you're like, hey, sell me power for cents, company will sell you. It's like, hey, if we do not sell it, we get to 0. 0 is a really bad number. That shall always have some number higher. And how can you sell this power? Well, during the evening peak, once the sun goes down and there is an evening peak, that head of the duck, it's brutally expensive power at that time, more than 8 times expensive roughly. So you can sell your power with 35 conversion efficiency more than well enough. Like you can buy cheap, sell it expensive, and you still have profit. And again, you are providing a service, which again, as more and more energy comes into the grid, services will increase in value because again, they are no longer entangled. Back in the old days, a core plant had inertia. Nobody had to thought about it. Nobody had to think. Now it's an independent service. So people will be like, hey, every household has solar. But again, that's too much surplus solar. You dump into this gives you the inertia. And during the evening time when we really need to chop that head. So at that point, it's like to flatten that head, it's like, I got this. It will only give you, let's say, for 3 to 4 hours of power, not like, pumped hydro. But again, it will give you that power and it will give you inertia. And we already invested in the asset to do these. It's already there. So that's why it works. Now, what are the alternates? Well, everybody is noticing that without inertia, grid does not work. And every Tom, Dick and Harry is focusing on magic batteries. So somebody came up with the idea, what if we have grid forming inverters, basically silicon bridge rectifiers and like all the technology, basically switching rectifiers that are working so well that they are actually acting as inertia. Now, I do not trust it. I do not like the idea of a country like India to trust black box technology. These are classified as black box technology, meaning you do not know how they work. And again, it's not even patented, it's a proprietary. So you do not know how it works. And one microcode failure, it could like poof. And India has learned the hard way that even military technology can poof itself. For example, our GPS was disabled by USA during, not our GPS, as in like we did buy it properly, but we learned it the hard way that if it's core technology controlled by someone else, it will be controlled by someone else. I do not like this idea. I do not like the idea of like ABB or General Electric coming like, hey, your grid, if we upload something bad, it goes poof. I do not like that. On another scientific level, remove the human cynicism out of it. Rule number 1 of engineering, complexity is the enemy of reliability. That's law of physics. You cannot break it. This is far more complex than a spinning mass and a hot bricks. So fundamentally, I do not trust the idea of grid forming inverters. Yeah, they're a bit more efficient, but again, almost achieving 95% efficiency with the technology that has been tested from 1910, it's far more comforting compared to magic blacks technology, where again, you can even have supply chain issue when the circuits are not being made quickly enough in Taiwan. I do not like it. And again, everything I talked about, this is being developed. This is at tier level 7. Again, technology is sorted. We know what to do. Right? It's just clever engineering, so to say. Tier level 7, it should reach tier level 9 in few years, and then we'll have all the problems sorted. So all the coal power plants that will be decommissioned due to coal price will change it. So this was my presentation on basically magic battery technologies versus real solution. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst a friend. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.